combination and
Combination and decomposition were the ones that we covered. All right. All right. So we did. So types of reactions is what this lecture is continuing on. And I believe we covered decomposition.
Correct. AB reduced down to A plus
Right.
B.
You got something big.
And then combination A plus
You're breaking it up into smaller pieces, and then combo.
A plus B yields A.
Well, we started. And this is also known as synthesis. And I want you guys to make sure that you know the different terminology, because depending on the author of the test that you might be taking, they might use different terms. And so this one is where you're taking smaller things and creating bigger things out of it. All right. Well, before we go into the last two types, which is going to be the focus of today's lecture, let's talk about combustion briefly. And we'll go into single and double replacement, which is going to take almost the whole period today to talk about those things, because I've given you a resource that you're going to be using, and we're going to be doing these things in lab this week too. All right, so combustion. Well, combustion, generally you start with some kind of a fuel, and the fuel often is some sort of hydrocarbon. And that's a term that the organic chemists like to use when they're talking about something that is made with hydrogen and carbon. And I'm just going to put X's and Y's as the subscript. Gasoline, oil, cooking oil, glycerin, anything like that is considered a hydrocarbon. Now, when you're burning something, we'll say that our hydrocarbon in this case is going to be a liquid. When you're burning something, what do you always need in order for combustion to occur? You need oxygen gas. And what's the formula for oxygen gas? O2. All right. So then we're going to create some products. And oddly enough, there's always specific products. There's complete combustion and incomplete combustion, two different types. We'll talk about the complete combustion first. The complete combustion, you always get water, and it could be, generally it's a gas because we're talking about hot stuff, right? Plus carbon dioxide, also as a gas, is a product of combustion. Right? So you've got some sort of hydrocarbon, a fuel. Oxygen gas has to be available for that reaction to occur. And you're going to have some water as a product and CO2. All right, our bodies, a good example of this is our bodies. Our bodies are internal combustion engines. The yogurt and granola that I had for breakfast this morning is my fuel. I breathe in oxygen gas. I exhale. What do I exhale? Carbon dioxide, we all know that, and I can show and I can prove to you that I'm also exhaling water vapor. That's how I clean my glasses, right? It's foggy on one side and not on the other because I've breathed on it. So I'm actually exhaling the water vapor and carbon dioxide. Our bodies are internal combustion engines, and the fuel we use in lab that you did last week, we looked at the caloric content of nuts versus bugles, a protein versus a carbohydrate, right? So those are things that we have to take into account. So incomplete combustion, you also use some sort of hydrocarbon. We'll say it's going to be in liquid form. You also got to have oxygen gas, but now the problem with incomplete combustion is you don't have enough oxygen gas for the combustion to be complete. And we still make water as a gas, but now we make carbon monoxide. And carbon monoxide and carbon dioxide are both greenhouse gases. Carbon monoxide, in addition to being a greenhouse gas, is also very toxic to humans. Is it a poisonous gas in and of itself? Is carbon monoxide poisonous?
Yes.
It will kill you, but it's not poisonous in and of itself. What happens is carbon dioxide has a molecular structure very similar to oxygen, and it will grab onto the hemoglobins in your blood and not allow the hemoglobins to transport oxygen from one organ to another, and basically you go to sleep, and then your organs start to shut down. So that's the stuff that comes out of the tailpipe of our automobile engines, right? Carbon monoxide. So that's not something you want to say and breathe for a long period of time. All right. Today we're going to focus mostly on single and double replacement reactions. All right. Single double replacement reactions involve substances in aqueous solution. So we'll just say XY is some compound, and we're going to call it an aqueous solution. Now, this is something that I know we spoke briefly about it on Wednesday, but an aqueous solution to a chemist is very different than an aqueous solution to John Q. Public out there walking around. One of the best ways to make an aqueous solution is with water. They call water the universal solvent. Now, why is water considered the universal solvent? What does that mean when they say it's the universal solvent? It dissolves most things, right? It dissolves most things. It dissolves most things that are ionic. And remember, we have two different types of compounds that we have talked about. Ionic, molecular, also known as covalent. And then we've also talked about acids, right? So those are the three categories of things that we talked about last unit when we're discussing naming conventions, the nomenclature, how to name these things. Ionic substances, the slang that chemists use for ionic substances, it's a salt. So most ionic substances will dissolve and dissociate in water. And that's why it's called the universal solvent, because almost every single ionic substance you put into water will dissolve and break up into its component parts. For example, we talked last week about sodium chloride, and it's a crystal structure of 3 dimensions, and that the water molecules will gang up on the charged ions. Sodium happens to be positively charged, and when it's hooked up to chlorine, which is negatively charged, the water molecules will turn themselves. Because water molecule is polar, and this side is positive and this side is negative, when they come up to the positively charged ion that is sodium in the crystal lattice structure that is sodium chloride, the charge that's positive on sodium causes the negative end of the water molecules to be attracted towards the sodium, and the sum total of a whole bunch of these water molecules ganging up on this ion pulls it off of the crystal structure. And so when we put sodium chloride in water, what we really have when we say we have an aqueous solution is we have water with sodium ions floating around in it and chlorine ions floating around in it. No more is there sodium chloride, the compound. It is now composed of ions that are floating around in the solution. And this is true of most ionic substances. Here's a ternary ionic substance. If I put this in water, it's going to break up into its component ions. What are the component ions that it's going to break up into? Lead. And what would be the charge on a lead ion? Based on this nomenclature for lead nitrate. +2, because you know that nitrate is -1 and there's 2 of them. So that must mean that the lead is +2. Then I'm also going to have these components in my solution. And I put them in a ratio of 2 to 1 because that's the ratio that the compound is. Now keep in mind, these are ionic substances. They do not exist in isolation by themselves. They exist as 3-dimensional lattice structures that when you put a piece of it in water, the water starts to attack it. Well, this is the positive ion, those are the negative ions. We have lots and lots of lead ions floating around. We have lots and lots of nitrate ions floating around. But if we looked at the ratio of lead to nitrate in this substance, it would be half as much lead as nitrate floating around. There would be twice as much nitrate ions floating around as lead because of the way that lead nitrate is added up.
So if you added hydrogen peroxide or water to that, then how does that?
That's a different kind of reaction. That's a molecular compound. We're focusing on ionic substances right now, but we'll come to that in a little bit. All right, so something else like calcium chloride, right? If that was soluble, and soluble to us as chemists, this word soluble, and we're going to be talking about this in just a minute. Soluble means that it will dissolve, but more importantly to us as chemists, that it will dissociate. And that's the key, that it breaks up into its component ions. So when a chemist says that an ionic salt is soluble, that means when you put it in water, it breaks up into its component ions. And no longer can you think of it as a lattice structure, that you have to think about the component ions. So if I put calcium chloride in water, what would be the ions floating around in here?
Calcium.
Calcium ions with what charge? +2. And then what else would I have floating around? I would have 2 chloride ions, and they're monatomic ions. Now don't think that because chlorine is one of those diatomic gases, that it's always Cl2, right? That's only when it's chlorine gas, when it's an ion in aqueous solution. And so we say that now we have an aqueous solution of calcium chlorine, and in your mind, this is the symbolic representation of what that means. When you see that calcium chloride aqueous solution, the microscopic perspective you should be thinking about in your brain is that that's what that actually means, that you have those ions floating around in solution. Now, it works with ionic substances, but it also works with acids. Acids and bases also dissociate, and most of them are very, very soluble, and they will dissociate in water. So something like hydrochloric acid, when I say it is an aqueous solution, that means no longer do I have just the pure hydrochloric anymore. Now I've put it in water, and once I put it in water, it's also going to dissociate into its component ions. So what would be the component ions of hydrochloric? Hydrogen ions, and what would be the charge on a hydrogen ion?
+1.
+1. What would be the charge on the chlorine ion? -1. All right. Let's try a different kind of acid. And how do you know that both of these are acids, that both of these formulas, there and there, are acids? Besides the AQ, there's another.
The hydrogen.
You got an H in front. So anytime there's an H in front, that generally means you're going to have an acid. Plus, there's no charge on these things, right? If you have an H in front and a charge, sometimes you consider that a polyatomic ion. So if you're talking about something like this, right, HSO4 minus, that's a polyatomic ion. It also is, when you get to Chem 152, we consider it has acid-base characteristics, but for now you're going to call it a polyatomic ion. All right, we put H2SO4 into water. It is also soluble. It'll break up. What are the component ions that H2SO4 or sulfuric acid would break up into? Two of those hydrogens, right? That's not H2 because it's not a gas. Those are an aqueous solution, and we're talking about individual ions. What would be the other ion that would break up into? Sulfate with a 2- charge. So you can see why it was super important for you to be able to recognize the polyatomic ions. It's also important for you to be able to deconstruct nomenclature, right? We did the nomenclature unit last unit. Now you know how to write these chemical formulas, and you know how to deconstruct the nomenclature of the units. All right, take out the document that I gave you. And these are solubility rules. I also posted this on Canvas. And this is your Corwin. So this is from Corwin. Now, I actually prefer the listing that, or the way that it's displayed in the Chem 151 and 152 books better than I like the Corwin way of he's showing this. But since we're using the Corwin book, we're going to learn how to use his display of solubility rules. Let's see if we can get this to look a little better on the screen. Is that better, or is it better with the light on?
It just needs to focus. Yeah, if you just
Focus. Let's try that. Auto tune. I think the printer was super faint. Oh, there we go. Is that better now?
working through it.
Okay. All right, so I think that's better. All right, so this is a table, and you have to, once again, it's super important for you to have your nomenclature knowledge in the back of your mind as you're looking at this table. It would also be helpful to have a table of polyatomic ions. Now, on the other side of the table, I gave you a periodic table, but you're going to see some of these ions here. What's that polyatomic ion right there? C2H3O2 minus. Acetate, that's an important one to recognize. NO3 is nitrate. Then we've got some ions here, some monatomic ions, and then we've got a polyatomic ion. So you can see that some of these are referenced based on what they're hooked up to. All right, so soluble, I want you to highlight the word soluble and insoluble. All right, so right now, this means that soluble means when it goes in water will dissociate. So if you put things that are in that part of the table into water, and we're going to learn how to use that part of the table in just a minute, they will dissociate. They are soluble. Things that are insoluble, that in water, will not dissociate. All right? So things that will dissociate, things that will not dissociate. Now, let's look at how this table is constructed so we can figure out how to use it. alkali metal ions. Now they're talking about a family here. What family on the periodic table are the alkali metals? The first row here. So these are the alkali metals. So what they're saying is things that are generally soluble are things that are hooked up to any of the alkali metal ions or the ammonium ion. What's ammonium ion look like? NH4, so you might want to put a little note to yourself on that. Ammonium ion is NH4+. So lithium, sodium, potassium, or ammonium are the things that are generally soluble. So what that means is when you're looking at something like, let's see, potassium chloride or lithium bromide or sodium sulfide, are those things going to be soluble based on this information?
Yes.
Okay, when I put them in water, they will dissolve, they will dissociate, because all of those are alkali metal cations. Or I could put something like this in water. Would that be soluble? Yes, it would. All right, so that's the first rule. Second rule, acetate ion, there's no exceptions. It's always, always soluble. So whenever you see acetate ion hooked up to anything, it will always dissociate. Same is true of nitrate polyatomic ion, NO3 minus. This turns out to be super important for us as human beings. Does anybody know where the biggest source of nitrates are that go into our groundwater, and therefore this nitrate, because it is infinitely soluble, cannot be taken out of the groundwater. So nitrates, once they go into our groundwater, they're always there, and they're also a known carcinogen. What does that mean, that it's a known carcinogen?
Cancer causing.
Causes cancer, absolutely. So if we put nitrate into the water, there's no way to precipitate it out. There's nothing that will take that nitrate ion. It is infinitely and always soluble. So what's the biggest source of nitrate that goes into our groundwater that we can't get out? Is it oil?
Is it,
Agriculture. What about agriculture would cause a lot of nitrates? Yes. Pesticides are part of this. It's more fertilizer, because fertilizers have a ton of nitrates in them, and also cow manure. And because in Arizona we tend to have feedlots rather than allowing the cows to run around on open grass ranges like they do in Texas. Here in Arizona we have feedlots where we bring the feed to the cow. They walk around on giant mounds of manure all day long, and then every time it rains, all that nitrates goes into our water supply, and it's impossible to get out. I'm a gardener, and I use fertilizer very sparingly. I use 0 pesticides. I'm a totally organic gardener as a chemist. That's kind of surprising, isn't it, that I use no chemicals in my garden? That should tell you something, right? And I use very little fertilizer, only very sparingly, and only on my trees 3 times a year when they require it, because of the fact that I know that nitrates are infinitely soluble. I'm sure you've heard about the Roundup issues. You know, the weed killer Roundup that you can spray and it kills almost anything in your yard? Well, guess what? It kills people too. It causes what's the Hodgkin's lymphoma? Thank you. And now there's all kinds of lawsuits about that, because guess what? You put that on the ground, it is soluble, it goes into our groundwater, we drink it. Okay, so those are issues that we have to all be aware of in terms of solubility. Halide ions. All right, the halides are chlorine, bromine, and iodine. What family are the halide ions? Chlorine, bromine, and iodine. Okay, those are the halogens, right? So those are generally soluble, except, now here's where the exceptions come in. Silver, mercury, or lead. So if silver, mercury, or lead are hooked up to one of the halogens, that means they are going to be insoluble, meaning they will not dissolve. So let's try a couple of practice runs on that one, and to learn using the solubility rules. All right, so let's look at SRBR. Is that going to be soluble?
yes.
Okay, so that would be an aqueous solution. How about lead chloride? No. Why is that not soluble? Most of the halogens are soluble. It's got lead hooked up to it, so that is not an aqueous solution. That would be insoluble, and it turns out that is pretty handy, because lead and mercury are stuff we don't want in our drinking water, right? We know that lead and mercury are bad for human beings. That's why they chlorinate water. One of the reasons they chlorinate water, because they bubble the chlorine right through the water. The chlorine grabs onto the lead and the mercury ions, pulls it out as a precipitate, and puts it at the bottom of what's called a flocculation tank at the water treatment plant. So that's a good way to use chemistry to treat our water, and chlorinating and brominating water actually does that very nicely, chlorine and bromine, because they pull lead and mercury out of the water. And the last one is sulfate ion. That is generally soluble except if it's hooked up with strontium, barium, or lead. And those are things that are insoluble. All right, so these are things that are generally soluble. Now, things that are insoluble, things that will not dissolve in water, anything that's hooked up to a carbonate, except Rule 1 exceptions. So things like those kind of things hooked up to carbonate, lithium, sodium, potassium, or ammonium hooked up to carbonate are the only ones that would be soluble. Another one that doesn't like to play well is chromate ions. Chromate ions are generally insoluble. Phosphate, sulfide, and hydroxide. Now the exceptions are the hard ones to understand here. And those are the ones, so these are things that generally are not going to dissolve in water, right? These are the exceptions that will dissolve in water. Okay, so now we've gotten that part of it done. Let's talk about, let's see, are we doing the double replacement lab first or the single replacement lab first this week? And
We have hydrogen.
what are we doing this week? I don't remember.
Lab.
Is it a double replacement or single replacement lab? I forget. Or we'll do single replacements first. How's that? All right, single replacement reactions generally involve, let me raise this up a little bit, generally involve what we'll call M, solid. That's going to be our metal, right? So something that's on the left-hand side of the periodic table, plus we're going to call AB some aqueous solution. Now AB can be an ionic soluble salt, or it could be an acid. So it could be either one of those things. Now this is the general form of the equation, like general form of slope of a line is y equals mx plus b, right? General form of single replacement reactions, you're going to have some metal, some aqueous solution that's either ionic salt in water that's soluble or an acid. And what happens is the metal, if, does anybody in this class know what IFF is? If and only if you're in calculus, right? So if and only if this metal is more active than this metal, so if and only if metal is more active than ion in aqueous solution, then a reaction will take place. And what happens is that metal there comes out of the solution as a solid, and you have a new aqueous solution made of M and B. All right, this is going to be our new aqueous solution. This is also known as a redox reaction. Does anybody know what redox stands for? Chemistry slang? Oxidation reduction. And what happens during oxidation reduction reactions? Anybody have any clue?
Electron is gained and then an electron is lost.
Very good. Electrons move. Right? And here's a good way to remember who's moving where. Oil, brick. Okay. Oxidation reduction is the loss or the gain of electrons. So oxidation is the loss, reduction is the gain. So there's a good mnemonic device to remember the difference between the two. All right, so that's the symbolic version. Let's think about the microscopic version. All right, so we got a container of liquid here, and we're still talking about single replacement reactions. And I'm going to use some actual real things that react in my example here. So let's try a solution of copper sulfate. It's going to be an aqueous solution plus some aluminum. All right. Now right off the bat, I say, this looks like it might be a single replacement reaction because I've got a solid aluminum, my metal, and I've got an aqueous solution of some kind. check on your rules, your solubility rules. Is this going to be soluble? Is copper sulfate going to be soluble?
No.
Well, here's the sulfate is generally soluble except if it comes into contact with strontium, barium, or lead. So is that going to be soluble? Yes, it is. So it's going to be an aqueous solution right there. So now, what that actually looks like. So there's the symbolic representation of my chemical reaction. Now we're going to pretend we're atoms and molecules, and we're going to go down into the solution and think about what's there. Well, I put my copper sulfate in there, right? What are going to be the ions that result when soluble copper sulfate goes into water? Copper ions with a plus what charge? It's a 1-to-1 with sulfate, plus 2, and you knew that because sulfate's minus 2 and it's 1-to-1. And then sulfate, polyatomic ions are going to be in there. And then in we're going to drop our hunk of aluminum. All right, here's our aluminum solid. And we're going to say it's a pretty large chunk, so it floats down to the bottom of the container. Now the aluminum, whenever you have a metal in its solid state, it has all of the electrons that it's supposed to have. So it has basically a zero charge. So it's not an ion, it hasn't lost any electrons, it hasn't gained any. It's neutrally charged, it's in its ground state. The copper, on the other hand, is deficient electrons. It's missing how many? 2 electrons. So it is electron hungry. If we take our activity series for metals now, and I want you to look at the activity series for metals here that I gave you on the sheet, and I want you to look at where aluminum and, what do we say, copper are. All right, so aluminum, there's aluminum. I'll highlight aluminum. Where the heck is copper? Copper is pretty low in activity. So this is high activity. This is low activity. Right? And that's why the little inequality signs are always pointing in that direction, right? So, who's more active, aluminum or copper? Aluminum is more active. So if we look back here, we say, all right, remember, if and only if the metal is more active than the ion in solution, a reaction will take place. Do I think a reaction is going to take place here between aluminum and copper? Yes, it is, because aluminum is more active on the activity series than copper. So now I have confidence that it will take place. Well, let's think about what's actually going to happen. Copper floats up here next to aluminum and it goes, hey, aluminum, I'm missing a couple of electrons, and I know you're more active than I am. Would you mind lending me a couple? And aluminum goes, sure, have some electrons. Metals love to give up their electrons, right? They're loosey-goosey with their electrons. So how many do you suppose aluminum gives to copper? 2. So then all of a sudden, copper now is no longer deficient electrons. It's going to go down to the bottom. It's going to make a solid copper, what we call precipitate. And what you would see here is once you put the metal into the solution, you would actually see some coppery colored stuff look like it was sort of growing and adhering to the outside of the aluminum. What do you suppose that coppery colored stuff is? Copper. Right? Because electrons are being exchanged. So the aluminum is giving up electrons. So is it being oxidized or is it being lost, the aluminum? Okay, so the aluminum is oxidized, right? Because it gave up electrons. Who's being reduced? Who's grabbing those electrons? Copper. So the copper is being, actually it's copper plus 2 ion, because that's different. Copper is being reduced. So it's grabbing electrons. So that's actually happening in the container. Electrons are being swapped between the metals. Now how do we symbolize that? We say, okay, well because aluminum gave up some of its electrons to copper, now copper is the solid thing that's part of the precipitate in the bottom of my beaker. See, I have to show that the copper has actually come as a precipitate out of solution, so I have to show that symbolically. Plus, now I have to make a new compound with the aluminum ions and the sulfate ions. And here's where, and I'm going to put this down here, you know that it's an aqueous solution, but now here's the key. And here's where nomenclature is going to come back and bite you right in the butt if you don't know what you're doing here. Just because copper and sulfate combine in a 1-to-1 ratio as reactants does not mean that they're going to do that as products. We have to write brand new nomenclature for products. So based on that information, what is the ionic charge of aluminum when it becomes an ion? Because now it has. It's a +3 charge, right? What's the ionic charge of a sulfate polyatomic ion? -2. So what's the correct nomenclature for aluminum sulfate? Al2.
SO4 3.
There you go. All right, and that is an aqueous solution. So what has actually happened? So the sulfate hasn't done anything, right? The sulfate's still in the aqueous solution. The aluminum and the copper have traded places. The copper's gone from being an ion in solution to being a solid, and the aluminum now is an ion in aqueous solution. So they actually trade places. That's why it's called a single replacement, because the metals are trading places after they lose electrons. Well, we still have to balance this thing, right? So now we got to look at balancing it. Well, I got 2 aluminums here and only 1 there, so I'm going to start in pencil in case I make any boo-boos. So I'm going to throw a 2 in there, right? Now, coppers are okay for now, but sulfate's not so much. How many sulfates do I have on the product side? I got 3. So what should I do the reactant side? Do I do it that way, or should I do this? Don't do that. You can't change nomenclature, right? You can only change the quantity of pieces that you have, right? All right, so now sulfate's okay, but now copper's not. So what should I do with the copper? Put a 3 there. All right, so now my equation is balanced. This is the type of homework that you're going to have to do as a result not only of the lab on single replacement, you're going to have to write quite a few of these, but also on the homework assignments for single replacement reaction. All right, that's the first type of single replacement reaction where you have a metal and a salt, ionic salt solution. Let's talk about a metal and acid. So this is still single replacement. Now we're talking about a metal with acid. Most of the time when you put an acid in metal, it's going to react, right? All right, so the general form is you're going to have, we'll call it M, solid is our metal, plus some kind of HX, right? And this is my acid. Start with my metal. This is just the general form of the equation. HX is some generic acid that I put H in the front of, and X could be a monatomic or a polyatomic ion. Now, as a result of the metal and HX combining, we get bubbles of gas. What do you suppose the bubbles of gas are when you put a metal into acid?
Oxygen.
Good guess, because H2O has oxygen, but think about the metal.
Hydrogen gas.
Hydrogen gas. It's actually hydrogen gas, which is, by the way, explosive, right? So you don't want to be smoking while metal is in acid, because it is very, very flammable. All right, so H2, and then generally you get some sort of metal in the solution. All right. So, for example, if we took something like, let's try sulfuric acid, aqueous solution, and we put in, let's see, we'll try some copper, solid. We still need to consult our activity series. Now we're consulting it for different metals. We still have the copper in mind. Where's our copper? But now what do I have to compare the copper to see if it's going to react? Look at your activity series. Not the sulfate. Look at the activity series that I gave you. Hydrogen. Hydrogen is what you have to compare. When it's an acid and a metal, you compare the metal to hydrogen. All right, there's our metal. There's hydrogen. Since this is more, this is less, right? Who's more active? Hydrogen or the copper? Hydrogen. So is that reaction going to take place? Nope, it will not. Will it? Hydrogen is more active. Nope, this has to be more active than the acid does. So that would be no reaction. Let's try another one. Let's try H2SO4. And that's important to know because on the exam you may get ones that are not going to be as reactive. Let's try some nickel. We'll drop some nickel down in there. Is that going to work? I'm not looking at copper anymore. There's the nickel. There's the hydrogen. Nickel's more active than hydrogen, so is it going to work? Yes, so we will have a reaction. Okay. In this case now, we're going to get, what is our products? hydrogen gas, right? And what else? Some nickel sulfide. All right, so we don't know what the charge is on nickel. Where the heck is nickel on the periodic table? It's a transition element. Well, we'll say that this is going to be a nickel plus 3, just to make life more interesting here. So if nickel's plus 3 and sulfate's minus 2, how would I write the nomenclature for nickel sulfate? 2 parentheses 3, right? All right, now I got to balance this beast. What should I do to balance it? Let me get this. 2 for the nickel. All right, we'll try that first. What else? I'll put a 3 there. But now that really messes up my hydrogen. I could put a 3 there, so then 3 times 2 is 6 hydrogen, 3 times 2 is 6 hydrogen, 3 sulfates, 3 sulfates, 2 nickels, 2 nickels. We're golden there, right? All right. Well, you need to also be able to write down what's oxidized and what's reduced. We'll go back to our first reaction, but let's look at this one first. So we're looking at hydrogen has changed somehow, right? And nickel has changed. And you should write the notation that I'm writing here on your notes, because you're going to have to do this for the lab. All right, so hydrogen has changed and nickel has changed. What I'm going to do is I'm going to write this. These are where I'm writing the redox half reactions. That's what this process is called. When you get to Chem 151, you'll have to know how to do this. And when you get to Chem 152, you spend an entire chapter writing redox half reactions and looking in depth at the redox of it. All right, so if you are in those 2 classes, make sure that you know what you're doing here. So we're writing the redox half reaction. So we're going to start with the nickel. We say 2 nickels as solid have changed to, I'm going to write these as 2 nickel ions, right? And we said the nickel ions had a plus 3 charge in aqueous solution. So you have taken the 2 nickel here, that are in solid state, they're in ground state, 0 charge, and I've put over as products, I've left some room, 2 nickel ions with a plus 3 charge in aqueous solution. Now I'm going to do the same thing with the hydrogen. I'm going to say, all right, I've got 6 of those hydrogen ions. Now, how did I know to write hydrogen ions there? How did I know that those were hydrogen ions I have?
Because they're in solution.
They're in solution, right? So they are all broken up. So you have to think in your mind's eye what actually is happening there. So 3 times 2 is 6 hydrogen ions. And they've changed into 3 molecules of hydrogen gas. All right, so those are the start of the redox half reactions. It's not the whole thing, that's just the start. And I'm going to continue. Well, if I look at the nickel, and I say, all right, if I just take individual nickel atoms. So here's an individual nickel atom, and there's an individual nickel ion. What did an individual nickel atom here have to do to become an individual nickel ion there? And I'm not looking at the coefficients, I'm only looking at nickel atom. What did nickel atom have to do to become nickel ion? Lose 3 electrons, right? So if each individual nickel atom had to lose 3 electrons, and there's 2 of them, how many total electrons are lost? All right, so that was the whole piece. That was everything that started out with all its pieces, plus 6 electrons. So there's the redox half reaction for the first part. Now we're going to write the redox for the second part. Here's the hard part. I'm going to hide the coefficients. Now we have a hydrogen ion that's becoming part of a hydrogen molecule. What does this individual hydrogen ion have to do to become part of that hydrogen molecule? It needs to gain
6.
no, 1 hydrogen ion. This hydrogen ion by itself, I'm not looking at the coefficients, remember I'm covering them up. This hydrogen ion right there, what does it have to do to be part of that hydrogen molecule? It has to gain how many? Well, if it's the whole molecule has to gain 2, but each piece has to gain 1. All right, so if there's 6 pieces, each of them gaining an individual electron, how many total electrons are gained? 6. So that's what we have to write on this side, plus 6 electrons. Now, you would label this with the oxidation reduction part of it. All right, so the oxidation reduction. Oxidation is the loss. Reduction is the gain. Is this the oxidation or the reduction? Is it gaining electrons or is it losing them? Losing them, so that is the oxidation, which you will have to label. And these are things you'll have to do in the lab and the homework, both. So if that's the oxidation, then this must be the reduction. Good way to check. Electrons lost has to equal electrons gained, or you did something wrong, usually in your nomenclature. Now let's go back to our original example. I'm going to rewrite it on a piece of paper here so it's a little cleaner so you can see it. The original single replacement reaction that we had here, which was 3 copper sulfates in aqueous solution plus 2 aluminum ions. And it might serve you well to rewrite this so that you have a clean copy to work from when we're doing this redox half reaction. All right, so there's the first example I gave you. Now let's do the redox half reaction for the first example. All right. So who changed here? Well, aluminum changed for sure, right? So we've got to draw arrows to aluminum. What's the other thing that changed? Copper. So now we got to write that there was 2 aluminums in solid state. That changed somehow. How would I represent what they changed into here when they're in aqueous solution? I'm going to put an AQ next to them for sure, but what am I going to show? How many of them did I make when I went over here into aqueous solution? 3, right? So if I take this unit and I break them up, how many sulfates do I get out of it? 3. So 3SO4, what's the charge on a sulfate polyatomic ion? 2 minus, and it's in aqueous solution. All right, you've got to have all of the appropriate symbology to communicate to the other scientists what's going on in your solution here. So the same thing with the top, but I'm going to write it a little bit lower. We've got 3 copper. Now how am I going to depict how those copper are existing? Are they charged ions? Are they ground states? Are they in aqueous solution? Are they solids?
They're ions.
They're ions. What's the charge on the ions there? Plus 2. Okay, I'm going to put that they're in aqueous solution. And they have created 3 copper solids. All right. Something I didn't tell you over here when we were doing this one that just reminded me is there are certain things that are always ground state. Elements in their natural form, like this, are ground state, but also all the diatomics are 0 charge. So hydrogen gas, chlorine gas, nitrogen gas, oxygen gas, all those are 0 charge. So when you look at hydrogen as a molecule in a gas form, it's 0 state. All right, so now let's think about what's happened to copper here. Let's think about individual particles first. Here's our copper ion, has a +2 charge, and over here it has 0 charge because it's in its ground state. What did this copper ion have to do to become a copper atom over here? Had to gain how many? 2 electrons. If there's 3 pieces, each piece gains 2 electrons. How many total electrons are gained? 6. Now I'm going to put those on the reactant side, or am I going to put those on the product side? Who has all the pieces it was born with? That one right there. So we have to keep the pieces that it was born with on that side. So we're going to put the electrons here, right? So that's the thing that's ground state. So it breaks up into those things. Now we're going to look at this one. What does an aluminum atom... Oh, wait a minute. I wrote that wrong, didn't I? No wonder you guys were confused. All right, we have 2 aluminum ions with a +3 charge in aqueous solution. Sulfate wasn't doing anything. All right, so what does an aluminum atom have to do to become an aluminum ion? Lose 3. If there's 2 of the atoms, each losing 3 electrons, how many total electrons are lost? 6. Where am I going to put those 6 electrons? On the product side. I could check. Electrons gained is electrons lost. Now we got to do the oil rig part. Who is oxidized and who is reduced? Remember, loss versus gain.
Oxidized is the aluminum.
Okay, so this is the oxidation. So then this must be the reduction. right, that's single replacement reactions using the activity series. Now let's talk about the two types of double replacement reactions. And this is going to be notes that you should, I will post these also on the lab. These are going to be super helpful when you're doing your lab homework and you're writing up your lab. These notes will be really, really helpful. All right, double replacement reactions, general form. You've got two aqueous solutions. I'm just going to represent them generically as A and B and C and D. All right, so we got A, B, and C, D, double replacement reactions. Well, what happened, and we all know this now because we've talked about solubility, I put A and B and C and D into aqueous solution. Those are the things that are now in the two different aqueous solutions. So it's not a metal in an aqueous solution. It's not a metal in an acid. It's two different aqueous solutions that appear to not have any solid particles in them. They're transparent or translucent. What do I mean by transparent or translucent? You can see through them, right? You can see through them. All right, so when you put these things together, what's the indicator that you have a chemical reaction in this case is that you get a cloudy solution or a precipitate is formed. So what things, now that's where our solubility rules come in. Now, these things have a different kind of a meaning. These things, no precipitate will form, so I want you to make some notes there. And here, insoluble, a precipitate will form. Right, so soluble, no precipitate, symbols you would use would be AQ. If it is insoluble and it forms a precipitate, then the symbol we use would be solid, and that's all right. So let's do it with some real life chemicals here. This pen is licking all over me. All right, so let's do some real life chemicals. Here's a very famous reaction. Lead nitrate in aqueous solution plus potassium iodide, also an aqueous solution. All right, put these things in to perspective, and this is the lab that you actually do. We give you a whole bunch of aqueous solutions. If I had my lead nitrate in aqueous solution, and I know that it's soluble, because nitrates are always soluble, always. So I know that it's soluble. That's soluble. Potassium iodide, let's double check that that's soluble. Iodine is generally soluble except if it comes into contact with silver, mercury, or lead. Is that silver, mercury, or lead? No, so that's soluble too. So now we are assured that both of our solutions are aqueous solutions. When I put this chunk in water, what are the ions it's going to break up into? Lead. What's the charge on the lead ions going to be? +2. What else is going to be in there? Nitrate polyatomic ions in a ratio of 2 to 1, right? All right. I put my potassium iodide. What's going to be resulting ions from potassium iodide aqueous solution? Potassium and iodine ions are going to come into contact. All right. So then what happens is you pour the whole thing together. All right, so now we're going to put all these aqueous solutions together, and it's a big, giant aqueous solution party. And some of these aqueous solutions, they show up to the party and they go, oh, you know what? There's no one here that I want to precipitate with, so I'm just going to stay in solution. The other ones show up to the party and they go, oh, there's a lot of choices to precipitate here. I think I'm going to get lucky and precipitate this evening, right? All right, so let's tell. And next time you go to a party, boys and girls, you can bring along your solubility rules and determine if, in fact, it is worth precipitating. So who's going to precipitate? Who's going to get together and make the solid come out of the solution? All right, well, who might be interested in each other? Are lead and potassium? No. Are they going to be interested in hooking up?
No.
No. Are nitrate and iodine going to be interested in hooking up?
No.
No. What about lead and nitrate? Do they want to be with each other?
Yeah.
Wait a minute. Wait a minute.
Hold up.
Nitrate is always soluble. Nitrate shows up to the party. Nitrate always goes home alone. Nitrate never precipitates with anybody. Who also is a very lonely ion besides nitrate? No, if silver, mercury, lead show up, iodine will precipitate. Acetate's an awful lonely ion. If acetate shows up to a party, does he ever precipitate?
No.
No. And you know what? I know I tell you these silly stories, but you know what? It perked you up and it got you listening, and you're going to remember it now. All right. So who might precipitate? Potassium might be able to hook up with nitrate, right? Who else might be able to hook up? Iodine with who? Who might iodine hook up with? Lead. All right, so lead and iodine might hook up. Now, here's the key. You have to write new nomenclature for the products, but the beautiful thing about this is there's no electrons changing, so the charges stay the same. Whatever the charges are as product or as reactants, they stay the same as products. So that makes your job about 10 million times easier when you're figuring out the charges and the nomenclature for the products. All right, over here we know potassium is a +1, nitrate's -1. Over here we know lead is +2 and nitrate's iodine's -1, right? So what is correct nomenclature for those two products? That's okay there, right?
PBI2.
We're good there, but it needs to be PBI2. All right, now let's see who the precipitators were. Here we go. Well, we know nitrate didn't do anything. How do we know nitrate didn't do anything? It's always soluble. Nitrate goes home alone, so right off the bat we know. Sorry, nitrate, you did not precipitate this evening. Let's look at iodine. Did iodine get lucky? Well, iodine's kind of picky, right? Iodine's picky. It's usually soluble. Usually iodine goes home alone, but who did iodine see in the corner? Said, hot dog, it's a good evening this evening. Lead showed up to the party. All right, now we need to balance this equation. How do we balance this thing? How do we balance this? Well, I got 2 iodines here and only 1 there, so what should I do? Put a 2. Now that messes up my potassiums, but then that fixes the nitrates, right? All right, so here's the key. You have to know that that is the precipitate based on solubility rules. These are the ones that are the lonely ions. These are the party animals. Carbonate's a huge player. Carbonate shows up to the party, he's always precipitating. Chromate, phosphate, huge players. Right? They're always precipitating. They're always forming precipitates. Okay? So whenever you see carbonate, chromate, or phosphate show up, you go, I'm suspicious, that's my precipitator, right? All right, so now we got to write what's called the ionic equation. And then we're also going to write the net ionic equation. So now we're going to take this thing, and we have to write the ionic equation out of it. I'm going to take all of the ions and show what I had in my solution. So I'm starting with this. I've got lead nitrate, so I have to write lead with a +2 charge in aqueous solution, plus 2 nitrates, 2 NO3 minus in aqueous solutions. Everybody see where I got the 2 for the NO3? Super important. Plus 2 potassiums with a +1 charge in aqueous solution, and you must write the charge and aqueous in every one of your notations or it will be incorrect. Plus 2 of those iodines, also in aqueous solution. And that's going to give me, I have to look at my products, aqueous solution versus a solid. A solid I'm going to leave as it is because those were the precipitators. Aqueous means those are the ions in solution. So 2 of those means I have 2 potassium ions in aqueous solution, plus, I'm going to go a little bit below here, 2 nitrate polyatomic ions, those lonely ions, nitrates. And I'm going to leave lead iodide together because that's the darn tootin' precipitator. And I can't write it as aqueous solution because it came together as a precipitate. What would you see? When you put all these things together, when I put it all together, all of a sudden you see a solid come out of the solution. I'll show you a video in just a minute what that actually looks like when you put them together. All right, that's the ionic equation, which has all of the component ions, including the states of matter, and what shows the precipitate. Now I have to create what's called the net ionic equation. And we're going to cross out what are called the spectator ions, and it's sort of like reducing an equation in algebra where you want to kind of cancel common terms on both sides of the equation, right? All right, so let's look for common terms. Well, I got 2 potassiums. Those are common, so I'm going to cross those out. What else do I have as common ions? Let's see here. Nitrate is a common ion. So now my net ionic equation just shows the stuff that we're interested in. It shows that lead came to the party. And lucky for lead, iodine also showed up to the party. And those little rascals, they precipitated. And your balanced equation needs to balance. Your ionic equation needs to balance. And your net ionic equation needs to balance. And if it doesn't, then it's usually an error in the nomenclature of your product. So if you can't get all 3 to balance, double check the nomenclature on your products. That's generally the issue. All right, that's the first kind of double replacement reaction. When you have 2 ionic substances, we also have double replacement reactions that are acid and base, also known as neutralization reactions. All right, so these are still double replacement. Now, Corwin is the only chemistry textbook author I have ever seen that decided that acid-base reactions should be their own category, and he has 6 categories. Generally, most chemists use 5. Single replacement, double replacement, combination, decomposition, and combustion. Corwin throws this as an extra one. Most chemists that I've ever met call it a form of double replacement reactions. All right. So we can have an acid, say something like good old hydrochloric acid, in an aqueous solution, which means it's not the pure stuff anymore. We've put it in solution and it has been dissociated. We're going to use a base. We'll say, how about barium hydroxide? We'll use as our base. Also an aqueous solution. Now we know that's an acid because you guys have learned how to name acids. How do we know that's a base? That's a base. That's the common slang word that chemists use. How do I know that's a base? By looking at the formula. Has the hydroxide on it. It is a metal hydroxide. And hydroxide is that OH. When you see a non-metal hydroxide like this is actually an alcohol. When you get to organic chemistry, these are all non-metal atoms. When you see hydroxide on non-metal things, that's an alcohol. So we don't do that in here. That's for organic chemistry. Our hydroxides always have to have a metal hooked up to them. That's why they're a base. So if it's a non-metal hydroxide, that's an alcohol. We're talking about a base in this case. All right. Acid-base reaction. Some of you may have heard of these things before. There's always 2 products you always get to acid-base reactions. What are the 2 products you always get? Salt and water. Very good. So salt plus water. All right, now the salt is not just plain old NaCl. Remember, salt is anything that's an ionic compound, a metal-non-metal combination. Well, we know the formula for water. It's going to be in liquid form. Well, if we took the OH and the H, right, that makes the H2O. What's the salt I'm going to have left? What's left after I take the H and the OH out of there? Barium chloride. So that's our salt, barium chloride. Now, just like in the other double replacement reactions, the charges remain the same. What's the charge on the barium ion here when it's in barium hydroxide?
2.
Plus 2. What's the charge on chloride ion always? -1. All right, so what should be nomenclature for barium chloride? BaCl2, and it's going to be an aqueous solution. So there's the liquid water. All right, so now we have to balance this. How do I balance this thing? Probably a 2 there. So now we've got 4 hydrogens and only 2 there. So I think we do a 2 there. And that fixes the oxygen too, right? All right, so let's do our ionic and net ionic equations based on this reaction. All right, so we look at the things that are aqueous solutions. Those are going to be the ions. If it's liquid or solid, it's going to stay as the whole molecule itself. So now I have to break up the HCl. So I have 2 hydrogen ions in aqueous solution plus 2 chloride ions also in aqueous solution. I You see why I have a 2 coefficient for both the hydrogen ions and the chloride ions? Everybody see why I have the 2 coefficient there? Yes? Okay. Now we're going to look at barium hydroxide. Plus, if I broke up one of those bariums, hydroxides, how many bariums would I get out of it? Not 2. It'd be 1 barium. What would be the charge on that 1 barium ion? Plus 2, and it would be an aqueous solution. What else would I get when I broke up one of those barium hydroxide pieces? I'd get 2, excellent, of those hydroxide ions, all right? So it's important that you see where these coefficients are coming from, because the equation has to be balanced, as well as remember, this is the ionic equation that we're doing now. All right, so now yields. Since this is aqueous solution, I have to put it as ions in the solution. So I'm going to have barium with a +2 charge, an aqueous solution plus, now I'm going down the bottom here for the second half of it. How many chloride ions would I get when I broke up one piece of barium chloride? 2 chloride ions, also an aqueous solution, plus my water, and since it's liquid, it's a molecule and I can't show it as being broken up. That's actually the thing that came together and caused the reaction to occur. All right, so now I have to cross out the spectator ions. And the spectator ions are exactly what they were in this reaction, were the ions that didn't do anything, right? Nitrate didn't do anything. Potassium didn't do anything. So now we got to cross out the things. Who's not doing anything here? Looks like chloride ions are spectator. Who else? Anybody else? Looks like barium ions are spectator ions also, right? All right, so now we're going to write our net ionic equation, which is 2 hydrogen ions in aqueous solution plus 2 hydroxide ions in aqueous solution gives me 2 water molecules. Now, anytime you have an acid-base reaction that's double replacement, it's going to look something like this. It might just have 1 hydrogen and 1 hydroxide making 1 water. It might have 3 hydrogens plus 3 hydroxides making 3 waters, right? But anytime you get this as your net ionic equation, you know that it's an acid-base reaction because the hydrogen came from the acid, hydroxide came from the base, and acid-base reactions always neutralize, and water is neutral. Okay? All right, now I'm going to show you guys a video that, actually it's a kind of a cool thing that you guys have never gotten to see because of the fact that this was something that Rio Salado developed. I was, between 2000 and 2006, I was a teacher, a chemistry teacher at Rio Salado. And that was when we were putting a lot of stuff online. Come on, computer, wake up. All right, Larry. Where are you, Larry? Oh, never mind. I got it. I'll make you happy. All right. So.
You just cross off the ones that are duplicated.
Yeah, I was trying to do it.
Okay.
Larry, I swear to God, that's even the video.
When I worked at Rio Salado, I was chair of physical science, and we had to develop labs. We didn't have the bandwidth at the time between 2000 and 2006 to deliver video lectures. There wasn't anything streaming. We had to send people CDs with stuff on them. We would also send them CDs with these labs on them that they couldn't do at home. Now, we would send them lab kits, and they could do some labs at home, but other labs they couldn't do on their own. So what I had my IT guys at Rio do was we taped a whole bunch of double replacement reactions. And what we did was it like something like silver nitrate, and this stuff, you could come together, you click on that, and it will show as you're adding one thing to another. Was there a chemical reaction when you add those two things together? No, there was no precipitate. So let's choose one. Okay, the iron ones are usually pretty cool. Those often have good precipitate reactions. Okay, now one is yellow and one is clear. Just because it's now yellow does not mean there was a reaction. You have to look for a precipitate. So in that case, there was not a precipitate. And I like the thumbnails that we did here because you can look at the thumbnails. You can see this was yellow and clear. This was just white and clear. And then the resulting solution was also clear. So let's pick another one of the iron ones. Yeah, this is one that's probably going to precipitate. No, that's not a good one. Let me pick another one. Here we go. Here's a good one. Okay. The original thumbnail, they're yellow and clear, the two solutions. Now when you put them together, clearly there's a chemical reaction there, right? So if we look at the original thumbnail and compare it, it was yellow and clear and this turned red. And then after you let it sit there for a period of time, you can see there's a precipitate in the bottom. It sinks down to the bottom of the test tube. And so what students had to do was they had to go through each of these, and it was sort of like they were doing the actual experiment. Let's see if we can find them. Yeah, so you got there's a good one. All right, so they're both clear and colorless when you put them in, and you put one into another, what's your evidence there that a chemical reaction has occurred? It turned cloudy, and now it's translucent, or no, excuse me, it's opaque, and you can't see through it. If you see the original chemicals, they were clear and colorless. It didn't make any difference, and then after you let it sit for a while, you can see the precipitate forms in the bottom. Okay? So this is double replacement reactions. Single replacement reactions we couldn't do on these kinds of things because the students had to have a metal and an aqueous solution or a metal and an acid, and it took much longer than these particular reactions did in order to take place. All right, let me show you where we are in our course. Let's see, Canvas. Does that do that to you guys? Does it kick you out if you does it? It does that to you? I thought maybe it was only teachers that did that too. All right, let's look at our labs here. Labs are we doing here this Oh, water of hydration. Okay, well, that's all right. That's actually, water of hydration is a decomposition reaction, so that will be interesting to look at. But then next week is single replacement reactions. The following week after that is double replacement reactions. So I will post this set of notes on the lab section so that you can go back and review. All right, that's all we got today.
Yeah.
Yes, nomenclature. If nomenclature is giving you any trouble, if it doesn't seem like it is for you, then for sure that's what you should do. Hey, what's up?
I sent you an email through Canvas about my grade on my nomenclature quiz.
Okay.
How on Canvas it says 21 out of 32, but I got on my paper I got a 32. I mean 31 out of 32.
You need to bring me the document.
Oh.
Who's next?
So, I missed the lab.
Oh, you're fine.
Just kick
Okay.
out.
It's allowed.